Imagine staring at an abstract, colorful two-dimensional entity, and then suddenly, out of thin air, its third-dimensional artifacts begin to appear. As you stare into the bewitching aesthetics of its intricate internal structure, a realization dawns upon you that you are quite literally staring at a 3D screen with a mystical mathematical object magically floating in thin air. This visualization is made possible by the topological and material innovations baked into our multi-utility display gadget christened the LemurBox. This device framework, built using frugal scientific easy-to-source materials, allows for several add-on hardware parts that allows the end user to manipulate its aesthetics as well as its functionality in multiple ways. With this background firmly in tow, we now introduce ourselves as HAL51.ai. An AI-first consumer tech startup sitting at the intersection of the three monocultures of geometric optics, artificial intelligence, and frugal science hardware. The rest of this 3D demo is dedicated towards covering the landscape of end-user archetypes and the associated real-world use cases in which our devices will be deployed in the near future.
End-user archetype, the coffee shop owner. The LemurBox can usher in a new revolution of hybrid reality displays into the food and beverage service industry at large. This entails generating digital assets of your offerings using easy-to-use scanning apps running on a simple smartphone and beaming them over the physical objects strategically inside the diorama chamber. Examples of these assets include a digital twin of a croissant, a blueberry muffin perhaps, How about a loaf of warm walnut bread, a freshly toasted sesame bagel, and hey, perhaps that latest bag of single-source coffee that you are introducing this season? In similar vein, a pizzeria owner can easily create digital twins of their pie of the day and entice new customers by showing off your latest creation. On a side note, that pizza does look sumptuous. Another scenario would entail grocers advertising the latest shipment of crisp black Oxford apples or even the latest Ruby Frost red apples to drum up more sales. End-user archetype, a supermarket or big box store operator worried sick about retail theft. Here too, our LemurBox can be used to display 3D digital twin replica of expensive items such as diamonds as shown here, or a gorgeous engraved wedding ring made of 24-karat gold and any other piece of pricey jewelry susceptible to theft. Thus, you are not only adding a new exciting way to capture the attention of the potential client but also curtailing the chances of a smash-and-grab type of theft. This scan and display paradigm also extends to other high-end items such as sneakers, bespoke designer handmade shoes, and eyewear models such as those sold by elite companies such as Ray-Ban.
End-user archetype, museum store operator. Museums all over the world are under immense pressure to repatriate the stolen historical artifacts back to their country of origin. If you are a museum curator, we believe that this is actually an exciting opportunity for you to start curating a treasure trove of high-fidelity digital twins of the historical riches in your possession. Displaying them in an interactive manner with our LemurBox framework of devices not just allows you to deliver richer and more meaningful visit experiences for your patrons, but also allows you to open up new verticals of revenue in the form of bespoke museum boxes and an associated smartphone application that enables one to take a virtual slice of the museum experience back home. End-user archetype, teachers and science communicators. Imagine a classroom where the impossible becomes reality. Imagine students gazing in awe at a 3D holographic rendering of a Penrose staircase, a mind-bending creation by mathematician M.C. Escher. Or perhaps they're virtually dissecting a complex geometric sculpture by George Hart, brought to life before their very eyes. These aren't mere pipe dreams. Holographic 3D animations have the power to ignite a spark of fascination in young minds, a fire that can fuel a lifelong love of STEM subjects. The pandemic highlighted the struggles of remote learning, particularly in subjects that rely heavily on visualization. But what if we could bridge that gap? By harnessing the power of 3D holograms, we can transform abstract concepts like nonlinear system dynamics or chaos theory into dynamic, interactive experiences. Imagine the thrill of a student manipulating a holographic model, witnessing firsthand the unpredictable beauty of a chaotic system. These mind-blowing visualizations, coupled with a fertile imagination, hold the key to unlocking a deeper understanding of even the most challenging STEM concepts, reversing the tide of COVID learning loss and igniting a passion for discovery. The revolution doesn't stop at the boundaries of math. Imagine a chemistry class where students can walk around a holographic molecule, peering between its intricate bonds. No longer will complex organic structures be confined to flat textbook pages. With 3D holograms, these molecules come alive, their spatial arrangement and functional groups bursting into vivid reality. This isn't just memorization, it's an immersive exploration of the very building blocks of reality. The veil shrouding the brain's complexities can finally be lifted with the magic of 3D holography. Imagine a classroom where synapses, the intricate junctions between neurons, transform from textbook diagrams into dynamic, holographic light shows. Students can witness the dance of neurotransmitters, the electrical impulses sparking across the connections. With 3D models, they can explore the bustling metropolis of the mind, navigating its vast neural highways. For astronomy educators, 3D holography is a game changer. Imagine a classroom where the enigmatic Schwarzschild radius, the point of no return around a black hole, transforms into a shimmering holographic sphere, its immense gravity warping the very fabric of space-time. Students can virtually peer into the event horizon, the boundary beyond which not even light can escape. These once abstract concepts become visceral experiences, igniting a fascination with the cosmos' most extreme phenomena. The wonders don't stop at black holes. 3D holography allows us to unravel the mysteries of cosmology itself. Students can explore the vast expanse of the universe, tracing the evolution of galaxies from swirling clouds of gas to majestic spiral arms.
Also, do note that the LemurBox framework lends itself naturally to the black background video formats created with Lightboard technology or math animation Python packages such as Manim. In what follows, we provide samples from two stalwarts of this art form, Stephen Burton from University of Washington and Grant Sanderson from the 3 Blue 1 Brown claim to fame.
Welcome back. So I've started this video lecture series on reinforcement learning, and the last 3 videos were at a very high level, kind of what is reinforcement learning, how does it work, what are some of the applications, but we really didn't dig into too many details on the actual algorithms of how you implement reinforcement.
To be a little more visual about all of this, we could plot each one of these probabilities as the height of a bar above the square in this sort of 3-dimensional plot. In some sense, this 3-dimensional plot carries all the data that we would need to know about rolling a pair of dice. As a general rule of thumb, anytime that you see a sum in the discrete case, you would use an integral in the continuous case. So let's think about what that means for our main example. Let's say we have 2 different random variables, but this time each one will follow a continuous distribution, and we want to understand their sum and the new distribution that describes that sum. You can probably already guess what the formula will be just by analogy. Remember, in the formula that we just wrote down, where p sub x is the function for the first variable, and p sub y is the function for the second variable, the convolution between them, the thing describing a sum of those variables, itself looks like a sum where we combine a bunch of pairwise products.